All right. Hey guys. Hey everyone. I'll do something a little bit different to this week. I'll make a couple of relatively short videos to go over some of the key ideas. This first one is really just kind of a review um, of what we did last time with a little bit of a twist. Not much. Actually, a clarifying point to help us get on our way, and this will help you complete the homework, I hope, and make a little bit of sense of what we were doing. So, what was the main problem was to maximize profits, function of capital and labor. And here's where I'm going to deviate a little bit. I'm going to call, or I'm going to put the power beta on L as opposed to 1 minus alpha. So the 1 minus alpha is just a subcase here where beta is equal to 1 minus alpha. Minus RK minus WL. So both alpha and beta have to be between 0 and 1. Okay, so that's fine. So then we're gonna maximize profits and find capital and labor. So to do that, we take our first order conditions. I differentiate profits with respect to capital and labor. Now, just a little bit of notation that P1, I'm going to call the partial of P with respect to K. It's the derivative with respect to the first argument. P2 is the partial of P with respect to L, derivative with respect to its second argument. Okay, so the first order condition says that those derivatives have to be equal to 0. Okay, so that's our necessary condition for finding a maximum. So let's go about figuring that out. So the derivative with respect to k is alpha z, k to the alpha minus 1, L to the beta, so beta is constant, minus r equal to 0. Similar for beta, it's going to be, or sorry, for beta, for L, I'm going to have beta z, k to the alpha, L to the beta minus 1, minus w equal to 0. So again, I have two equations in the two unknowns, k and L. And so let's start with, I'll just number these. I'm going to start with equation 1, and I'm going to solve for, let's say, k as a function of L. So equation 1 says that alpha z, k to the alpha minus 1, L to the beta is equal to r. I'm going to divide both sides by alpha z. So that I have k to the alpha minus 1, L to the beta is equal to r over alpha z. Again, so a little trick that I like to use is to start giving these things names. So I'm going to call that A, so that my first order condition here tells me that k to the alpha minus 1, L to the beta, is equal to A. Then I can divide both sides by the L to the beta, and I have k to the alpha minus 1 is equal to A L to the minus beta. So I can work with it like that. I can flip them around however I want to flip them around, right? So if I flip both sides over, I have k to the 1 minus alpha is equal to 1 over A times L to the beta. Okay, so, that's not too bad. I can then raise each side to the 1 over 1 minus alpha power. And I have then that k is equal to 1 over a, 1 over 1 minus alpha, times L to the beta over 1 minus alpha. So that is k as a function of L and a function of A, which is related to the real interest rate or to the cost of capital, sorry, R, the parameter alpha, and our productivity, Z. Okay, so we'll keep that equation for k handy. The next step, and by the way, if you want to keep making your life easier, which I like to do, it is true. I mean, if you do this too many times, it gets hard to keep track of what everything is, right? But if I want to simplify, I can just make this a constant b, right? 1 over a to the 1 over 1 minus alpha, I can just call b. And I can eventually come back and make sense of what all these parameter values are. But I could write k as b times L to the beta over 1 minus alpha. So now, my first order condition for labor was, well, there it is, this one here, equation 2. So I'll rewrite it down here. We had beta z, k to the alpha, L to the beta minus 1 is equal to W. So, we can work with this a little bit. I'll do something a little different than I did last time, which is, first, let me do this. So we have beta z k to the alpha is equal to W times L to the 1 minus beta. So I divided both sides by L to the beta minus 1. That leaves me with L to the 1 minus beta on this side, right? So if I divide by L to the beta minus 1, down here, I have L to the minus beta minus 1, which is L to the 1 minus beta. So then what I want to do is I can start plugging in for what is capital, right? So what is capital? Well, I'm going to get rid of this W, so I'm going to have beta z over W times k to the alpha. Well, k is b times L to the beta over 1 minus alpha, all to the alpha power. And that will equal L to the 1 minus beta. So I'm going to move this over. I've got beta z over W times b to the alpha, L to the beta alpha over 1 minus alpha is equal to L to the 1 minus beta. So I can then divide both sides by one of the L's, right? And I've isolated the L. So I can divide here by L to the beta alpha, 1 minus alpha, divide this one. And these cancel out. Beta z over W. That term b, a constant, the alpha, is equal to L to the 1 minus beta minus beta alpha over 1 minus alpha. Okay, so again, this gets really messy with the exponents. And really this problem at the end of the day is really just an exercise in some very simple algebraic manipulations and keeping track of your exponents. right? Being able to manipulate the exponents and being comfortable manipulating those exponents when they're expressed symbolically as opposed to as a particular number or root of L. So, you can go about simplifying that power however you want, but I've now figured out what L is. L is beta z over w, b to the alpha. That whole thing then to the 1 over 1 minus beta alpha over 1 minus alpha is what I end up with. So that's it for L. And once I have L, I can plug that back into my equation for K, right? So K is going to be B times this thing, all raised to a power. Now, that's a little bit tricky, right, with all the exponents, and you get all sorts of messes of stuff. But in the homework question, we have a simplified version where we just have some particular values for beta and alpha, for alpha and beta. And so the algebra and everything doesn't really turn out to be that bad. Now, the reason why I did this more elaborate version is that when you get to graduate school, you'll start to notice that you do a lot of these problems, similar problems, and you do a lot of them. And so I always found it was easier to work out the general solution first, which I have here. And then I can simply plug in the values of alpha and beta and z, w, and r, and I can arrive at the answer. And it provides a good way to kind of check my work after the fact. Okay, so that's it. So I just wanted to go through a solution there. Try it on your own to replicate what I've got here at least, and follow my steps. And if you can do that, the homework is going to be a breeze. So I'm going to have one more video where I'm going to talk about sufficient conditions to find an optimal solution in these cases. And we'll apply it to this particular case and see what we get.